Afternoon. I'll be talking about switching mode power amplifiers today. And I'm Don, and this is also by Professor Peter Asbeck, Shintaro Shinjo, Yongpayo Han, and Joanna Yan. Now our motivation is the next generation of transmitters have to support high data rates, like Verizon and Nokia told us, and while maintaining high efficiency, because you're going to want to use them all the time. So instead of having 4 PAs, like we see here on an iPhone 3G, we'll have 1 PA, and that PA will have to be broadband, sustain a wide variety of coding and modulation schemes, so that we will need something perhaps, let's say, a switching mode PA. Now, we're looking at 20 megahertz bandwidth LTE signals, and probably soon to be LTE advanced. For infrastructure, looking at ranges 10 watts or above, but as we also see, there's a 3 to 5 watt range. There could be a sweet spot for these voltage mode Class D amplifiers for the micro base station size that has a range of about 300 meters. But of course also handsets where the average power is 27 dBm. We always have to remember there's a peak to average power ratio associated with these, so that the peak power is going to be 3 to 6 dB higher in this case, and in the case of the base station amplifiers it can be 6 to 8 dB higher. So we'll first start with signal generation, where we're thinking of, okay, here we have an RF input, which we would normally input to the power amplifier. So instead, we will input a discrete, or some people might see, digital RF input to the power amplifier. In this case, this looks very similar to a pulse width modulation scheme, and in fact, that's what this particular example is. Then we'll have an RF switching PA, which in this case looks like a souped-up CMOS inverter, which is actually part of the motivation for this. And then an output filter. In this case, this is a resonant series LC circuit, and there's the resonant frequency. Now, there's numerous options for implementing each of these blocks, and also the signal encoding should be matched to the RF switching PA. Certain topologies of RF switching PAs can accept certain types of modulation schemes, particularly digital schemes, and certain others can't. The reason for the voltage mode Class D is primarily because it can accept almost any. Particularly, it can do pulse width modulation. Many of the switch mode PAs do not accept pulse width modulation. When you see simulations under pulse width modulation, the efficiency drops or the distortion is very high. A voltage mode Class D can support pulse width modulation, which has one property of it, probably has certain forms of it, have the least amount of power out of band. So you're spending less time generating out of band energy, which might be reactive, but that's very good for efficiency. So we'll talk about gallium nitride FET, voltage mode Class D, in both micro and pico cells, also for handsets, where we can use CMOS devices, and we'll investigation for filter efficiency, and also broadband gallium nitride PA development. So let's first start with the gallium nitride voltage mode Class D. This is the topology. Again, basically a power inverter. In the simplest iteration, you have a P-channel device, an N-channel device, in turn driven by another inverter and another inverter. Now, we'll hopefully will not get into the curse of Earl McEwen of Tropian that found that you have to start cascading a lot of these stages together because like the effective power added efficiency of each gets in the way. And so you won't want to have something where you're generating 5 watts of output power and 2 watts of driver power. We hope that avoid that. So here you would look at the waveforms associated with it. This is very simple. It's sort of, let's say, it's a square wave voltage generator, although it could be pulse width modulation. So you look at the upper and lower. And of course, because this passes through a filter, basically what you are doing is you are generating one portion of the sine wave with the upper transistor and the other portion with the lower transistor, and you get to fill it in. What's nice about it is you can see that that can apply to a lot of different waveforms that you can imagine, so it's relatively simple to come up with ways you think you could make these 2 transistor switch to produce the sine wave, which is really dependent upon this resonant network here. So when we look at ways to do this, we're thankful to Mitsubishi Electric, which has made their foundry available for no cost, which is really good because that saves a lot of money. And in fact, not even no cost, is that the students have been able to make schematics and layout suggestions, and the engineers at Mitsubishi have done the layout. which is also a very nice service to provide, and maybe we're spoiling our students as a result. They have several different gate lengths. Okay, these are relatively long gate lengths, by the way, but FT for, let's say, this 0.7 micrometer gate length of 17 gigahertz is actually very, very high for that long of a gate length device. And the same thing down here to the 0.25 micron device has a very, very high FT. And that means they could be used as switch mode devices. Particularly, let's say, even the 0.7 micron gate length would be very robust. You won't blow them up, and you can still switch them at a gigahertz. So we have the high side drive problem because of two reasons. One, there are no p-channel devices in gallium nitride. There's only n-channel devices. And two, you'd like this VDD voltage to maybe be something like maybe positive 48 volts. So the low side device isn't bad. These are depletion mode devices, by the way. So here, oh, well, you may only have to drive to minus 2 volts. Here, if you really want to do it without a floating drive, you get these ridiculous voltage swing. You do not want to drive this to, let's say, 2 volts below 48. You will simply waste all your power in the drive, and it probably wouldn't last very long. So we certainly don't want to use just that simple method, because this is not like 3.3 volt CMOS. This is something closer to 48 volts. So we'll need to solve that problem. And it's been a problem with switch mode at PAs for a long time, particularly this topology. So you do a bootstrap high side drive. This is basically a diode here. There's a resistor here, a capacitor here. In a way, what you're doing, and this V sub S can be chosen so that the swing here is not any larger, basically gate to source, than it needs to be, and it floats. But there is one disadvantage, there's a resistor here. Okay? So that means during one of the strokes, you're wasting power through that resistor. Okay? But you still can get 68% efficiency with this at 1 gigahertz simulated. Hopefully, we'll get this die back soon because it's been taped out, and we'll test and be able to demonstrate that. The reason we use the resistor is because it's a safe way to drive, and therefore we can try lots of different methods of driving this. There are some other more sophisticated techniques, but we wanted to do this one because it allows for a very broad frequency range too. It's not very frequency selective. Okay, so now let's look at the test setup. Use a pulse generator, in this case from Agilent, which can go up to 13.5 gigahertz. So then you can generate all kinds of different waveforms, particularly if you want to try to modulate something at a gigahertz. You have plenty of modulation bandwidth. Unfortunately, right now we'll need these optical modulator drivers in order to drive this at a sufficient speed, because this output here is basically a small signal output. So we'll use optical modulator drivers, which we need to eliminate, to drive the gallium nitride voltage mode class D into an external output filter. The output filter is not on this die. It is far too large to place upon it. Hopefully we'll have that in a month or two. Now, the other technique that people talk about is envelope tracking. I certainly talk about it a lot anyways. Okay, so this is where you use a drain modulator to the RF amplifier so that you have not a DC voltage to the RF amplifier, but the envelope voltage. And the idea is, what if you made this envelope amplifier one of those voltage mode class D amplifiers? Then you could have this RF amplifier, let's say, operating at 10 gigahertz, and this one here maybe has a 500 megahertz bandwidth switch mode envelope amplifier. That could be very useful. Think of it, you could go up to 60 gigahertz that way with a 500 megahertz bandwidth. Maybe a 1 gigahertz bandwidth someday. So this is how we are going to do. We're going to take a 200 megahertz voltage mode class D and use it as a buck converter. Actually, it's somewhat crossed between a buck converter, maybe a class S modulator. So here, because much more of the energy is allowed to go through, because you only need a single inductor here, we can get 80% efficiency even with this resistive bootstrap circuit here that we use. And what's nice about it is that you can get a wide variety of duty cycles out of this, and it maintains this relatively high efficiency. So we can take the same topology and turn it into a drain modulator, as well as turning it into, let's say, an 800 megahertz voltage mode class D amplifier for a small base station. So that's great. We can get two uses out of the same topology. Now, this is the CMOS voltage mode class D. What's nice about it is you can use P-channel, N-channel devices, and because this is a much lower voltage, you can simply switch this with respect to ground as well. So that's two major advantages. Voltage is lower, and you can have N and P-channel devices. Now, in this case, you do need some large capacitors associated with this that kind of bungs up the die because you spend a lot of die area with capacitors. But you do have these issues associated with bond wires, and because you're switching a very low impedance PA, very, very fast, it doesn't take very much inductance in order to start ringing, so we don't want that. So we end up with these rather large MIM capacitors and also have to reduce the shoot-through current. But when we said it's only 3.3 volts, we find out that you can generate very little power that way, not even enough for a handset. So we're going to have to stack it. That was the unfortunate part, realizing that you have to stack it. But fortunately, we've done stacked PAs before. In cooperation with ST Micro's foundry, we built stacked PAs. In this case, this is single-ended. This is not switching. But we found out that, hey, we can stack PAs in order to improve the output impedance of this and also basically get higher voltage for the same current so we can get more output power so that you can achieve that 27 dBm, which is really maybe you need 2 watts of peak output power in a CMOS process. So you end up stacking them up 4 ways, both top and bottom. So you have 4 P-channel devices stacked with 4 N-channel devices. In this way, you can keep the voltage across each reasonable, still have a reasonably small die, and increase the voltage. So that's a very nice thing. You can do this while we're using a relatively long gate length because it's inexpensive, okay, to go out to do this. And that's part of our motivation here is that you can even use this relatively long gate length process that costs less, a lot less than TSMC and is quite low lead time. So these are the simulated results. We'll be getting this divide back first. Drain efficiency is 60%, power rated efficiency 46%. You can see there's a gain problem here. And output power is 300 milliwatts. Okay, still needs some more output power. Here's the PMOS and the NMOS drain voltage. And of course, these stack up as you move up the stack. And it really is, again, it's using a capacitive voltage divider with resistors in order to equalize those voltages so you don't overstress any one. So now let's switch gears. We'll go to a broadband gallium nitride PA design. So this is where we're going to be using resistive feedback. First of all, you stack 2 devices. Okay, all right. You really have to do that for GaN? No. But if you're going to do it for broadband, that's what you're trying to do. So you have this RC feedback network in order to improve the bandwidth. And so you can take a single device, and this is without fancy balins and fancy tunable matching, and you can get a wide band RFPA, in this case maybe 600 megahertz to 1600 megahertz, hopefully 400 megahertz to 1800 megahertz on a die, which is a very big advantage because then you realize you're not depending upon a tunable matching network that needs to work over this wide frequency range. And that was from the last CWC review. So we now have this in Mitsubishi GaN, which is a better GaN. So this will be coming out soon. So it'll be 400 megahertz to greater than 3 gigahertz. Really proud of that. We haven't got it back yet, but we will soon. Efficiency greater than 50%, at least for single tone, and an output power of 10 watts. What we dream is that you'll have 1 PA lineup. That's all you need, and you just change the filter diplexer LNA on the output. So that way, Nokia Siemens Networks only needs to stock 1 PA lineup, and all they have to do is maybe change the filter diplexer LNA. Again, these are simulated results associated with this. Basically, what you're looking at is this is a feedback technique for basically controlling what would often be the Miller capacitance of the device, because you would see gate to drain, where you can see, first of all, you put 2 in series, so you get less. And then with the resistive feedback, what that does is that equalizes particularly the S parameters over a very, very wide frequency range. It does reduce the gain, but that's why you stack 2 in series, because you get the gain back. Okay. Okay, so this is the chip size. Again, about 2 millimeters by 1 millimeter. Again, gracefully provided by Mitsubishi. What you can see here, there's various capacitors here. These are shorting bars. So we have a laser, and Professor Buckwalter has shown us how to use it so that we can tune this, in case we make a mistake, to get that wide bandwidth that we're talking about by basically being able to add and subtract capacitors with these bridges that we can cut with our laser we have upstairs. So we're also looking at a push-pull stacked PA design. Again, because push-pull amplifiers have this nice property as they self-terminate the second harmonic, which is important for efficiency and bandwidth. Okay, and then greater than 60% efficiency and greater than 20 watts power output. They have greater output power because it's using 2 devices. So we have high expectations for that. And it also is inherently broadband. Again, it uses a different technique. Here, you are terminating the harmonics, self-terminating the harmonics in the 2 devices, so that basically what you've done is you can create it basically each one is basically carrying a half a sine wave, and the other side is creating the other half side of the sine wave. And if the capacitance of the device is relatively low, which is a nice property of gallium nitride, this concept works very, very well, even though their output power is quite high. So we're going to have some posters that we'd like you to go take a look at. You could talk to the individual students to get more details about all the things I talked about today. We have the voltage mode class D design, poster out there. We also have an application for voltage mode class Ds in an envelope amplifier with hopefully really wide bandwidth. We also have broadband PAs designed with the feedback, and we have millimeter wave PAs designed with stacked MOSFETs. And we also have something we did not talk about, but well, these 2 here we didn't talk about, receive band noise and envelope tracking PAs and how to eliminate that. And that includes my talk.